I'm going to wrap up this discussion of resonance in this lecture by first looking at how we can kind of summarize resonance forms into what's known as a resonance hybrid. Um, Now, I'll just kind of start really simple and then get a little bit more complex in terms of the number of resonance structures. So I'll go back to like our very first example of resonance. We looked at this allylic carbocation. We used a curved arrow to show how the electrons move. Now we have the resonance structure for this. Now, what a resonance hybrid does is it kind of summarizes these two resonance forms. And you'll notice that the pi electrons are drawn between these two carbons on the left and between these two carbons on the right. So the way that we can take the resonance, the hybrid of that, is we use these dots to show that, well, sometimes it's there and then here. And then we can also indicate that, well, in one resonance form, there was a positive charge over here. So I'm going to use a partial positive symbol. And then on the other resonance form, the other carbon was positively charged. So I use a partial positive symbol there. And that basically kind of describes that, well, all three carbons are sharing the pi electrons, and the carbons on the ends are partially positive. Again, indicating that it's not always like the left carbon is not always is not plus one, or the right carbon is not plus one. They kind of have these partial positive quality rather than a whole positive charge. Let's look at another example here. So if I were to draw the resonance form for this structure, one way I could do that is I can move these electrons there, move these there, and move those there. And if you look at between the two resonance forms, um, the carbon-carbon, the double bonds are between different carbons each time. So how do I summarize all of that? Well, I'm going to use those dots again. So sometimes there's a double bond there, sometimes there's one there, and so on and so forth. I'm going to kind of go all the way around here. And that's our hybrid form for those two resonance structures. Now I'm going to dive a lot deeper into this in our when we talk about benzene and aromatic compounds a little bit later, but we'll kind of come back to that. And let's look at one more example here. Now this is going to be a pretty complex one. We're going to draw a lot of resonance forms here. So notice we have an allylic carbocation. I'm going to start here and move those pi electrons towards that carbocation. Now I want you to make a mental note of where the positive charge is. And in fact, I'm going to highlight it. Now I can draw another resonance form. I'm going to move this here. There's a plus charge there. And again, make a mental note of where that plus charge is. And I'm going to keep on going. I'm going to move this here. And now the plus charge is here. And then we can do one more. And now the plus charge is here. I want you to look at those 5 positive charges. What do you notice? Notice that each carbon at some point in these 5 resonance forms, each carbon has gotten that plus charge. And notice where the positions are of the double bonds is that each carbon, or if you pick a set of two carbons, each set of two carbons has gotten at least one pi bond in one way, shape, or form throughout these five resonance forms. So how do I summarize all of this? So my hybrid is going to look like this. I'm going to use the dotted lines to indicate that the pi electrons are moving all around this ring. What do I do with that positive charge? I can say the same thing has happened by putting that plus charge in the middle, indicating that at some point, at pretty much what this is saying is that every carbon in that ring has some sort of partial positive character. I mean, we could draw them around them like this, but it's kind of more convention since every single carbon has that plus charge or has had that plus charge to draw by putting it in the middle. And that indicates that at some point in time, or that all the carbons are sharing that positive charge. Now, the last thing I want to look at is the effect that resonance has on hybridization. So I want you to copy this structure down here. And I'm going to ask you kind of a review question. What is the hybridization of that nitrogen? Now you look at that and say, well, I got four regions of electron density. It's got to be sp3, right? Well, here's kind of the interesting thing. When scientists were able to actually measure the bond angle of this compound through various instrumental means, they found the bond angle was about 120 degrees around that nitrogen. Now, what kind of hybridization does that correspond to? That nitrogen, the bond angle is basically saying that nitrogen is sp2 hybridized. So how do I explain that when I have four regions of electron density? Well, the way we're going to explain that is with resonance. Remember one of our common patterns? A lone pair right outside a double bond, or kind of, it's not technically an allylic atom. That nitrogen is not allylic because the carbon-oxygen double bond is not a carbon-carbon double bond, but it operates on the same principle where I can move those lone pairs basically by showing that resonance form. I'm describing the lone pairs on nitrogen as delocalized. That's just a fancy word for saying they're moving across multiple atoms. They're not stuck on the nitrogen. And I can see that because now the oxygen has an extra lone pair. Now what I want you to do is look at this resonance form right here. Tell me what the hybridization is of that. Now there's three regions of density. So resonance here and the delocalization of those electrons, of those lone pair electrons, show us how that nitrogen can have a 120-degree bond angle, and we would consider it to be sp2 hybridized. In fact, if I were to put an example like this on an exam and ask you, what's the hybridization of the nitrogen? You would be incorrect in saying it's sp3, but because of resonance, the correct hybridization of that nitrogen is sp2. Now let's look at a little bit more of an orbital explanation for this. So again, I'm going to draw the same compound here. Now, if we're saying that that nitrogen is sp2 hybridized, That means it's got three hybrid orbitals around it. There's sp2, there's another sp2, and there's another sp2. So all the red ones are sp2 hybrid orbitals. Now, what's the one remaining orbital that I haven't talked about yet? The unhybridized p orbital. The lone pair is in an unhybridized p orbital. Now, what do you see right next to that nitrogen, right next to that lone pair? Well, you got another sp2 hybridized atom, and then you have a third sp2 hybridized atom right there with that oxygen. What happens when you have three atoms right next to each other? Each of them have an unhybridized p orbital. Well, I'm going to redraw this one more time. I'm just going to look at the unhybridized p orbitals. So nitrogen's got one, this carbon's got one, and that oxygen, I'll just kind of hide it right there. And all three of them are consecutive and parallel. Remember, we talked about that before. So it's a lot more stable for this nitrogen to be sp2 hybridized, have its lone pair in an unhybridized p orbital, and be conjugated with the carbon-oxygen double bond. So let's look at a few problems and then we will stop here. So for each of these, we're going to write some lone pairs and we're going to indicate if they are localized or delocalized. Localized means we can't move them through resonance. Delocalized means we can move them in resonance. And then we're going to predict the hybridization. So let's look at A. So each nitrogen here is going to have a lone pair. I want to start with this one here. Just going to draw an arrow. Can I move that lone pair by resonance? Can I do this? No, we cannot do that because I'm moving towards an sp3 hybridized atom. So the lone pair on this nitrogen, we say is localized. And so now I just find its hybridization as normal. There's two hydrogens on it, there's another bond to a carbon, and then a lone pair. So 4 regions of density is going to make that nitrogen sp3. Now let's go to the other nitrogen. This lone pair, I can delocalize because I can draw that there, and then I can move those pi electrons there. And I can keep on going, but I just want to just demonstrate this one point of showing that the lone pair is delocalized into the ring. So let me just show the resonance form for that specifically, and then we can answer the question of hybridization. So now if we look at the hybridization of this nitrogen right here, it only has 3 regions of density. So we would say it's sp2. Now let's look at B. I'm going to draw the lone pair in on that nitrogen. Can I delocalize this into the ring? Now I want you to kind of look very carefully because you might say, oh, well, yeah, sure, I can take this here and move this here. If I draw the result of that, what's the hybridization of that nitrogen? Technically, it would be sp, but this is impossible. Why is that? Well, what's the shape, or what's, I should say, what is the bond angle of an sp hybridized atom? The bond angle is 180 degrees. Can a six-membered ring have an angle of 180 degrees? Absolutely not. If you don't believe me, build a model kit of it. You won't be able to do that. So you cannot localize the lone pair into the, or I should say delocalize, I'm sorry, delocalize that lone pair into the ring. Which brings me to a very important trend that you should remember. If there is already a pi bond to an atom with a lone pair, then the lone pair cannot be delocalized. It's stuck where it is. So this nitrogen has a localized lone pair and it's already sp2 hybridized. Can't change its hybridization anymore. Now in the last one, I'm going to draw the lone pair in on this nitrogen. Notice there is not a pi bond to it, and I can draw a resonance form like this. And I can keep on, I can draw more resonance forms. I'm not gonna, I'm not gonna show all of them, but this demonstrates that that lone pair is delocalized. And if I look at the hybridization for this nitrogen right here, what is that? It's sp2 hybridized. So that's how we label the original nitrogen there as sp2. And that will conclude this for this unit.